Okay, thank you for the presentation and thank you for the invitation to the organizers. I am going to speak about non-regularity, which is inherent to Finslerian geometry, that is, which appear even if we try to make the things as smooth as possible. This is relevant for Finsler spacetimes and other extensions for general relativity, but also in standard relativistic spacetimes, as some Finslerian elements are implicit at some points. I will do a brief survey with some prospects on these four topics: foundations of general relativity, fiber-wise smoothability of Lorentz-Finsler metrics, the Einstein-Hilbert-Palatini equations, and boundaries, conformal and causal. Here I have selected one paper which contains most information about each one of the topics. Anyway, here me and also some of the co-workers, Miguel Sanchez, Mocaponi, Flores, and Herrera, will be in the meeting and we can discuss further for small groups. First, I will start with some basics on Finsler geometry, Lorentz-Finsler, and regularity. I will consider Minkowski norms, which are usual norms except for two conditions. The first one is positive homogeneity, that is that we do not assume reversibility, that the norm on a vector may be different to the norm on minus the vector. And the second one is strong convexity, that is the indicative, the unit sphere must have second fundamental form greater than 0. In particular, this indicatrix is smooth, eventually it may be analytic. However, there is a trivial fact that we cannot avoid, is the fact that if the square of the norm is C2 as 0, if and only if it comes from a scalar product. In a Finsler metric, we will put a pointwise Minkowski norm in a smooth way in a manifold. Typically, we use the square of the Finsler norm, which will be positive to homogeneous, and the Hessian of this square up to a factor and half is called the Hessian at each tangent space is called the fundamental tensor and provides the second fundamental form in each direction. As a consequence of non-reversibility, one have that the distance induced by the Finsler metric may be non-symmetric, and then one has forward and backward balls, Cauchy sequences, geodesics, completeness. So it is not the same thing to go from the center to the point than the other way around. Okay. In particular, for example, for Cauchy boundaries, we have that when the distance can be extended to the boundary, but perhaps the distance from a sequence to a point to the boundary is equal to 0, but the distance from the point to the sequence is different to 0. Okay? Also, as a consequence of this previous property, when we consider the product of a Finsler manifold and any other manifold, for example, on the interval of R, then the product metric is not smooth. It's not smooth in the Finslerian part when it vanishes. Okay. Finsler metric induces a nonlinear connection seen as an horizontal distribution, which complements the vertical natural one in the tangent bundle. This horizontal distribution is invariant by positive homosthesis, and well, in coordinates is determined by the coefficients of the nonlinear connection, which has a suitable coordinate transformation, homogeneity, and in a natural way provide the natural basis of the horizontal space at each point. They have a standard expression for the Finsler metric. I will not go into the details of these coefficients, but I would like to point out that if the coefficients are not defined on the 0 section, okay, in principle, and if they were smoothly extensible to the 0 section, then the nonlinear connection will be a linear connection, okay, and then linear in the sense of an affine and causal connection, okay. If we want to put all these things in the Lorentzian setting, we will start with the definition of a cone. A cone will be a smooth hypersurface embedded in a slit vector space, which is conic, that is invariant by positive homothesis, salient if the vector belongs, the minus the vector does not belong, and strongly convex, that is the second fundamental form is positive definite, except in the radial direction where it is degenerate. Such a cone determines an interior, a convex domain, which is then called the interior of the cone, and it becomes the boundary. And a Lorentz-Minkowski norm is defined then in the closure of this interior, that is the cone and the interior, is smooth there. It vanishes only on the cone, is positive to homogeneous, and now it has a signature, which is Lorentzian, say plus minus minus. Okay? Such a norm has a strongly concave indicatrix, so we have a reverse triangle inequality, and the things work more or less as in the natural Lorentzian case, in the case of scalar products, with the difference that here the unit vectors, the indicatrix, is only a strongly concave hypersurface, but not necessarily an hyperboloid. Okay? This hyperboloid can be interpreted as the space of the observers, if we consider one of them, the tangent space to this indicatrix. Okay, would be a space that end up with a negative definite Euclidean product. Okay. This is consistent with what happens in relativity and Lorentzian scalar products, where the orthogonal hyperplane to a vector can be also identified with this tangent space. But well, in the case of Lorentzian scalar products, one has the scalar product defined on all the vectors of the vector space. Okay, we could make this also in the case of Lorentz norms, but notice that in this case we will have two disconnected parts of the indicatrix, one for time-like vectors, another for space-like ones, and the time-like directions will not determine the time-like the space-like directions. Okay, in the case of scalar products, just the time-like directions determines all the scalar products. Then a Lorentz-Finsler metric is just to put a Lorentz norm, a Lorentz-Minkowski norm at each point, so that we will have a Finsler spacetime with a cone structure, which provides the like direction, and an interior domain with the time-like directions. Okay? Well, this is just the basics, the notation we are going to use. Let us start with the first point. Is about the foundations of general relativity and the Ehlers-Pirani-Schild approach. Well, this is a classical approach which provides some axioms and gives a foundational support of standard general relativity. These axioms concern light propagation, introducing concepts such as mesaitis, echoes between particles, and things like that. And at the end, these axioms provide a differential manifold structure with a cone structure in the spacetime. There are also some axioms on free-falling particles, and these axioms provide a projective structure. And finally, there are some compatibility axioms, and where you obtain a Lorentzian metric up to a constant. Well, in principle, Finsler spacetimes are then excluded by these EPS arguments, because the cone structure must be a quadric, and then at the end must be Lorentzian, okay? And the projective structure must be compatible with an affine connection, and then, it's not a nonlinear one. And in particular, we will have a space-like geodesics. So in principle, these actions only would permit Lorentz-Finsler metrics which are compatible with Lorentz metrics. For example, a Lorentz norm with a quadratic cone, on the so-called Bergwald metrics, which admits nonlinear connection with at the end affine connections. However, a closer look at the axioms shows that the quadratic cones are obtained because the EPS arguments introduce the differentiability as zero of some product of radar coordinates. And at the end, this turns equivalent to ask for the smoothness of a norm of the square of a norm at zero. Okay. Also, if one consider the actions for the affine connections, the actions at the end, the coefficient of the nonlinear connection would be extensible to zero and would be the coefficients of a linear connection. So in principle, we can either maintain original EPS actions and exclude Lorentz-Finsler metrics, or to weaken these actions. Okay. From my personal viewpoint, I think that some, say, principles more or less down to earth and which are compatible with the Lorentz-Finsler settings are the following. First, when one tries to introduce a geometric theory for spacetime, one is making some linear approximation, which is implicit to the to the notion of inertial frame of reference. In fact, this inertial frames of reference satisfy two axioms. One is an affine character, that is inertial frame of reference introduce 4 coordinates. The first one called time, like in the whole spacetime, and the change of coordinates between two of them is affine. And second, interchangeability. That is, if we consider 2 inertial frames of references, the time coordinate for one of them varies with the time coordinate of the other, as the time coordinate of the second varies with respect to the time coordinate for the first one. And analogously with the other space-like coordinates. Well, admitting these 2 axioms, okay, the second step is to deduce all the linear models which are compatible with these axioms. And these linear models are characterized by essentially the transition matrix between the 2 affine reference fields. Because of the previous axioms of interchangeability, this matrix must satisfy these properties, matrix and the inverse. Here we must have the same element than here, and here the transpose than here. So if one makes computations, compute all the matrices satisfying these properties, and obtain a series of groups which depends on a parameter k. When this parameter k is positive, one obtains the classical orthogonal group. When it's negative, the Lorentz group, which is infinity Galileo group. And when it is zero, the dual of Galileo group, which was called Carroll group by Lévy-Leblond. Here in these 4 classes, perhaps the Lorentzian one is selected because the square root of minus the parameter is interpreted as the supremum of speeds between inertial frames of reference. And so this is the case, the only case where the supremum is finite but not zero. Once we have arrived to these models and well, perhaps selected the Lorentzian one, the third step is to drop the initial idealized symmetries. That is that if we drop the affine character and regard it only as an approximation, we will obtain general relativity. And if we drop interchangeability and we consider it just as an approximation, we obtain a Lorentz-Finsler metric. Well, either by these axioms or either by the consideration of differentiability, I will consider in the remainder Lorentz-Finsler spacetime as something reasonable to work with. However, we will have to consider questions about regularity which appears in these Finsler spacetimes. First, if one looks for physically motivated examples, and first noticeable one is Bogolowski metric, where there is a breaking of the Lorentz symmetry, which leads to Lorentz norms. This was called by Cohen and Glasgow very special relativity because we are reducing the Lorentz group. Now there is a natural step from very special relativity to general very special relativity, or just very general relativity. And the Finslerian elements here were identified by Gibbons, Gomis, and Pope, and later, well, studied by a lot of researchers. Typically here appear singular directions, and it is not so important the singular points in the manifold, but the singular directions. And these singular directions appears essentially because of two reasons. One, because it's a physical requirement for the picking of the symmetry. And second, because of some practical choice of examples. Okay. I would like to emphasize that such non-smooth fibers in the tangent space typically can be approached by fiber ways, smooth Finsler spacetimes. Okay. In order to justify this, let me recall you the way how to construct Lorentz, a general way to construct Lorentz-Finsler metrics. Essentially, all of them can be seen as the difference of two metrics, one Riemannian and the other Finslerian. Okay, and satisfying some generic conditions of compatibility, say the intersection of the indicatives is non-empty and transverse, and there is an hypothesis on the sign of the fundamental tensors. Now, any cone structure can be also recovered from a Lorentz-Finsler metric, essentially by a similar procedure of difference. The procedure is as follows. If you consider a cone structure, we are putting at this point of the manifold a cone. Okay, well, this is automatically time orientable. We have a time-like vector, and we can choose one, and also choose one form such that the one form of the vector is equal to 1. Okay. Now, if one focus on the hyperplane where the one form is equal to 1, and on the cone and consider the intersections, one obtains here on hypersurface, and this hypersurface can be projected in the direction of the vector field in the kernel of the one form. Okay, then this hypersurface will be the indicatrix for some Finslerian metric defined on this kernel, and the cone structure can be then recovered as a difference between the square of the one form as the square of this Finsler metric. Okay, what can be recovered in this case in this way, but the direction of the time-like vector will be non-smooth by this construction because of this problem of regularity of set of the norms. However, this happens only in a direction of each point, and this can be smoothened with no problem, even approximated analytically. Okay. This is widely applicable to handle singular directions in practical cases. For example, if I consider stationary and static spacetimes in the classical Lorentzian setting, and we want to translate this to the Finslerian setting, because a stationary spacetime is intrinsically defined as a spacetime which admits a time-like Killing vector field. Locally, this means that it is standard stationary, and standard stationary is just a metric on the product R by a manifold S, which is independent of the coordinate T of the R part, and where the Killing vector field corresponds with this associated vector field. In the static case, the intrinsic definition says that the orthogonal distribution of the time-like Killing vector field is involutive. And in the local version for the standard spacetime, that there are no cross terms. Okay? These definitions, the intrinsic definition, can be extended naturally to the Lorentz-Finsler case. Stationary means, again, to admit a time-like Killing vector field. And static, well, that the orthogonal distribution to the vector field is involutive, but the orthogonal now in the fundamental tensor, we have to choose here, again, the Killing vector field. Okay. These spacetimes can be characterized locally, again, But this local characterization is not, with some models and so, is not the same one that if we try to transplant the Lorentz local characterization. Indeed, if we try to transplant what is a standard stationary spacetime or a standard static one, we will write a product with a Finsler metric, which is written more or less in this way, on a product R by S, okay? And these cross terms would not appear in the static case, okay? However, such type of metrics are not smooth whenever the part in the Finslerian, the part of the vector in the Finslerian component is equal to 0, okay? However, again, this happens at each point in one direction of the indicators, and this can be smoothened and can be approximated by stationary and static spacetimes, as in the previous case. Okay? Well, now we have recalled the importance of this question on the directions. We are going to apply them to the setting of Einstein-Hilbert-Palatini equations. Okay? Well, now we are wondering about the field equations which should be satisfied by a Finslerian spacetime, taking into account the variational approach, say, a la Hilbert. Okay? In the classical general relativity, one considers the Hilbert functional is the integral of the scalar curvature. One has then the Einstein equation and contracting the equation Ricci equal to 0, just in the case of the vacuum that it will receive. The Palatini approach, which was also introduced by Einstein, consider the same functional, but now where the variables are not only the metric, but the affine connection, which is not regarded as the Levi-Civita one. Okay. Then, in the Palatini approach, one obtains an equation as Einstein's for the symmetrized part of the Ricci tensor, and some connections which may involve torsion. The Palatini approach supports classical general relativity because if we consider a metric which is the solution of the Einstein-Hilbert equation, Euler-Lagrange equation, then the Levi-Civita connection is the unique torsionless Palatini solution. Okay. Of course, the torsion, the solution with torsion can be also constructed, and they depend on essentially on one form. In the case of Finsler spacetimes, one can try to make something similar. Okay? Then, in the case, the Ricci tensor in a Finslerian manifold is a Ricci scalar which lives on the tangent bundle. But well, we can integrate this Ricci scalar on the indicators and then to make something similar to the Hilbert functional. The Euler-Lagrange equation has some parts which is as in the classical case, and other terms which will appear a tensor which is called the Landsberg tensor, which is characteristic of Finslerian geometry. Noticeably, these equations are not equivalent to Ricci equal to 0, even though, of course, in the Lorentzian case, this is equivalent to Ricci tensor equal to 0. By the way, the Ricci tensor equal to 0 is a derivable equation, but it is not a variational equation. Okay. We can go from this Hilbert approach to the Palatini approach, and this Palatini approach here is even more necessary because from the physical viewpoint, as we have many more nonlinear connections than linear connections, one can wonder if the free fall which would be provided by some nonlinear connection must use the same nonlinear connection as the nonlinear connection associated to the Lorentz-Finsler metric, which controls proper time, length, something like that. And from the mathematical viewpoint, in the corresponding functional, there is a natural splitting of the dependencies because the rich scalar depends exclusively on the nonlinear connection. But in the case of classical Lorentzian approach, we have to put here the scalar curvature, which depends on the connection on the contraction with the metric. Well, these equations has been studied recently in a detailed way. We just will comment some results. This was done in collaboration with Miguel Sanchez and a PhD student, Fidel Villaseñor. The first one is that from a PDE viewpoint, we have local solutions, but these local solutions are defined on the tangent bundle. And so it is not clear if just one of these local solutions will have a nonlinear connection, which is defined on the whole causal cone for the Lorentz metric. Okay. The second fact is the metric equation nicely does not have the Landsberg component. And so this is closer to Einstein's. Even more, if we assume that the Lorentz-Finsler metric and the nonlinear connection are smooth and defined on the whole causal cone of the Lorentz metric, then this becomes equivalent to Ricci equal to 0. Okay. Notice that this equation is a scalar equation. This is not the same trick as in the Lorentzian case. This is one has to make and to solve some technical problems. Okay. Indeed, the results here are different from when in Lorentz and in Riemannian signatures. If we consider the affine equation, that is the equation obtained by Barry in the nonlinear connection, then this has an entangled expression, but some nice properties. The first property is that, as in the Lorentz case, we have some classes of solutions, in the sense that if we have a solution, then we can essentially add one form, and then we will have another solution. And in each class of solutions obtained in this way, we have only one with no torsion. However, in the Lorentzian case, one has only one class of solutions. What happens in the Finslerian case? Well, in the Finslerian case, if we consider fiber-wise analyticity, that is that at each tangent space, the norm is analytic outside the zero direction, that is the indicatrix is analytics. Okay? And we assume that the solutions are defined on the whole causal cone, then we will have only one analytic class. Okay? Of course, any Lorentz metric, any smooth Lorentz metric is fiber-wise analytic because the scalar products are always analytic. Okay? It is worth pointing out that analyticity is not related here to Gottschiko-Valeskaya theorem. It is because some original technique is valid precisely in indefinite signature, not in the Riemannian one. Moreover, in the Lorentzian case, we don't have not only one class, but this class is exactly the class of the Levi-Civita connection. What about in the Finslerian case? In the Finslerian case, the class of the Levi-Civita connection is a solution if and only if a contraction of the Landsberg tensor, which is called the mean Landsberg tensor, which essentially is one form, is equal to 0. Okay? So we don't have always in these highly Finslerian cases, we don't have always that these nonlinear connections associated to the metric is a solution, and in this case, even the time-like geodesics differ. However, the like-like geodesics still agree on the cone. Okay? So summing up from all the conclusions, I would like to stress from the viewpoint of regularity, the essential hypothesis that the metrics must be defined on all the causal cone, and that smoothness is a natural property to obtain results, and perhaps in the tangent bundle, the natural property will be some analyticity, okay? And well, this is about these equations. Is this okay? Finally, some words about boundaries. We will start with a purely Riemannian problem. The problem is the following. Consider a complete Riemannian manifold with a smooth boundary. It is easy to check that if the interior of the boundary is convex, in the sense that its 2 points can be connected by a minimizing geodesic, then the boundary must be infinitesimally convex. That is the second fundamental form with respect to the inner in the direction must be positive semi-definite. Otherwise, if it were negative definite in some point, for example, if we took this part here, we could find counterexamples to the convexity of the interior. Okay. Now, one can wonder at what extent the converse holds. That is, if it is infinitesimally convex, if it will imply that the interior is convex. Bishop gave a positive answer in an old paper under the smoothability C4. Okay. Borisenko and Olin pointed out that Bishop technique does not work in the Finslerian setting because he makes some reduction to a two-dimensional problem which is not valid there. In collaboration with Caponio, Germinario, and Bartolo, we gave a positive answer for C11 metrics and in the Finslerian setting. This positive answer is given in 2 steps. A first step is to prove that the infinitesimal convexity implies local convexity, where local convexity means that if I consider any point of the boundary and take the exponential of the tangent space, this is not crossed by the boundary of the manifold. Okay? And then once this local convexity is established, one can prove that the completeness of the manifold with boundary implies convexity. That is a system of the minimizer, and the minimizers will not touch the boundary because of this local property. Even more, completeness can be weakened in the Finslerian setting because in the Finslerian setting we have forward and backward completeness, and so which are not equivalent. Here, the optimal hypothesis is to ask for the compactness of the intersections between the forward and backward closed balls. Okay? With this hypothesis, this works. Well, when we obtained this result, we thought that this was the optimal result. After looking at results like Melanie graphs with the C1 metrics and by other people here in the audience, I don't dare not to say that this is optimal. And perhaps somebody here can reduce here, can lower here the regularity. Anyway, let me tell you some consequences for spacetimes. The first one is about standard static spacetimes. Come back again with them, okay? Yeah. Here, it is simple. It is easy to characterize the causal simplicity of this spacetime. Recall that causal simplicity means that the causal future and past of the points are closed. This is equivalent to the convexity of the metric on the space-like part and the space part, okay? But not the initial metric, but the coefficient between the initial metric by the lapse, by the function with multiplied dt squared, okay? As I have said, this is a simple computation. Now, as a corollary of our previous result on Riemannian manifolds with boundary, if we consider an open domain with a smooth boundary in this S part, and we consider the cylinder obtained with this domain and multiplying by R, which is included in the standard static spacetime, it will be causally simple if and only if the interior is convex, and this is equivalent to the fact that the boundary of this domain is infinitesimally convex, okay? And, well, this can be shown to be equivalent to the fact that the boundary of this domain in the whole spacetime is convex for the like-like directions. This first result can be extended to standard stationary spacetimes. And standard stationary spacetimes, all the things work in the same way, except for two facts. The first one is that causal simplicity becomes equivalent to convexity, but convexity not for a Riemannian metric as before, but for a Finslerian metric, Finslerian metric like this one, which is constructed from the elements in the standard splitting, okay? So the result here is of the equivalence in the case of a cylinder, okay, for causal simplicity is equivalent to infinitesimal convexity for this Finslerian metric for the boundary, okay? The results like this has applications for example, asymptotically flat spacetimes, where one can prove that Lattice balls are causally simple. They are like convex, but not time convex, and provide some physical interpretation. But what I would like to emphasize here is that this boundary, which I have used before in the spacetime, can be regarded in a natural way as a conformal boundary. And Finslerian elements appears even in these classical stationary spacetimes, okay? This is also translatable to the causal boundary, which is intrinsic and is valid for any spacetime. Indeed, if we compute the intrinsic causal boundary of stationary spacetimes, then they are described in terms of Finslerian elements, the Finslerian versions of Museman and Gromov compactifications. This includes also the Cauchy compressions with this non-symmetric distance and these boundaries, Cauchy boundary, which is forward and backward. And the picture of this boundary is something like this, where each one of these elements correspond to something essentially Finslerian, okay? So all these Finslerian subtleties appears even in the classical level. On the one hand, a nice thing is that, well, these previous conformal and causal boundary developments can be more or less extended in a direct way to stationary Finsler spacetimes. And that in general, the transition from Lorentz to Lorentz-Finsler for cones and causality is not so different, because the Finslerian ingredients were implicit previously. However, this produces a warning. The warning is that when general structures, which generalize classical spacetimes as Lorentz metric or Lorentz spaces, are extended to or are extended beyond the boundary, then these Finslerian issues appear always, okay? And in fact, there is a work in progress by Burgos, Flores, and Herrera showing that this happens. Well, that is all. Thank you for your attention.